Alright, so here we are with the end of our Chapter 1 and 2 test review. Yikes. So, in exercise 43 and 44, we need to solve the equation. Super. So all it's saying is there's a quadratic that's equal to 0. First thing we would want to do is factor, if we could, but notice that we are trying to then find out what multiplies to be 13, which is just 1 and 13 because it's prime, and never will that become negative 6. So, in that case, we're going to use the quadratic equation. So, in your quadratic equation, you've got x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. And in this equation, a is going to be 1, and b is negative 6, and c is 13. So, we're going to plug those pieces in. So instead of, I'm going to rewrite it. We're going to have negative, but then b is negative 6, so potentially positive 6. And then we'll have negative 6 that will plug in to b squared minus 4 times 1 times 13. And that's going to be 2 times a. Alright, so if we evaluate, the first thing that we simplify is the discriminant underneath the square root. So negative 6 squared is going to be negative 6 times negative 6, which is positive 36. So we technically get 36, and to that we're going to subtract 4 times 13. And 4 times 13 is 52. And so we're talking about the square root of 36 minus 52. Or the square root of negative something. Oh, 16. Okay. So, in that case, negative 16, the square root of 16 is 4, but that negative makes the result 4i. And so if we rewrite, given that idea, we're going to have 6 plus or minus 4i over 2. And then since both of these are even, that means that you can actually do 3 plus or minus 2i, because we divided both of them by 3. And so that's our solution. Not really anything exciting. Complex numbers. Alright. Then in number 49, we need to find all the real zeros of the function, finding exact values whenever possible, and identify each zero as rational or irrational, and state the number of non-real complex zeros. Yikes. So, in order to do that, I'm going to start off by factoring if I can. So I can definitely take out an x squared. And so we'll have x squared, but then our leftovers of x squared minus 10x plus 23. And 23 is prime, and so we can't do anything to multiply to be 23 and add to be negative 10. So we're going to have to do the quadratic equation again with an a of 1, a b of negative 10, and a c of 23. So that means that we're going to have x equals negative b, which is negative 10. Don't have the green anymore. There it is, negative 10. And plus or minus square root b squared, so negative 10 squared minus 4 times a and c. And a is 1 and c is 23. And that's going to be over 2 times a, which is 1 as well. So evaluating our discriminant here, we're going to have 100 minus 4 times 23. That makes 92, so we have the square root of 8 as our value there. And so officially rewriting it, we're going to have positive 10 plus or minus the square root of 8 over 2. Alright, so that doesn't really, okay. So it turns out the square root of 8 is actually equal to 2 square roots of 2. How do I know that? Because 8 is actually 2 times 4. And so the square root of 8 could actually be the square root of 2 times 4. And then in square root land, you can actually split up the square roots if they're multiplied. And so you can see you have a square root of 2 and a 2 left over. So because of that, we actually can divide each of these pieces by 2. So 10 divided by 2 makes 5, and then 2 divided by 2 makes a 1. So 5 plus the square root of 2. Plus or minus the square root of 2. So these ones here are complex or irrational, because there's no fraction that can make that, especially because it has, oh, it's not an I, it's just irrational because it can't be made into a fraction. We also have these ones up here. When does x squared equal 0? So x squared equals 0 if we square root add an x of 0. And so x of 0 is going to be irrational, even though it's a 0. So those are rational. And then, let's see, there were 2 of those and 2 of those, and it's a 4th power. So that means that there are not any complex zeros. So no complex zeros, 1 rational, 0, that's a multiplicity, and then 2 irrationals. Again, because you can't make them into a fraction, square root of 2 is irrational. So if you throw that in, it makes things immediately irrational. Alright. I'm just going to double check that I answered all those pieces of that question. Find all the real zeros. So that's these 2 here. 3 technically. Finding exact values whenever possible, so that just means keeping it as a square root if you can. And then zeros are, okay, there we go. So, in the next one here, we're going to find all the zeros and write a linear factorization of the function. That just means factor it. And of course, each of those terms are a linear equation, which is why they say that. So, how do we factor something that's in 4s? I could factor by grouping, but it looks like that's not really going to work. So we're going to have to do the terrible rational root theorem. So we have factors of 12 and factors of 5. So 12 is 1, 2, 3, oh man, that's a lot of them, 4, 6, and 12. And 5, thank heavens, is prime, so 1 and 5. Which means that we have to check all of these zeros, which again, the easier way would be to plug in this equation into y equals, and then make your table set so that your independent is ask. And if you do that, then you're going to be able to just type in these numbers and see when you get 0. So our zeros are going to be an option of plus or minus 1 from 1 over 1, plus or minus 1/5, plus or minus 2 from 2 over 1, and plus or minus 2/5, plus or minus 3 and 3/5, plus or minus 4, plus or minus 4/5, lots of 4s going on, plus or minus 6, and plus or minus 6/5, which is totally lovely, and plus or minus 12. Wow. Okay, so again, a lot of these, it would be annoying to have to actually plug in algebraically, and so that is why we're going to have the calculator do it. So, taking a look at each of these, remember these are the zeros, so if we write it in linear factorization, we're just going to do x minus what we have. We will have 3 of them because it's x to the 3rd, so our linear factors are going to be that. And so I need to type in the equation 5x to the 3rd minus 24x, x squared plus x plus 12. Let's make sure I didn't miss any negatives or anything. Okay. So then my table set is already on independent as ask instead of auto. Going to my table. You can delete all the x's that may or may not be there. So I'm going to try 1, not a 0. Negative 1, not a 0. 1/5, not a 0. Negative 1/5, not a 0. 2, Negative 2. Make sure that you're doing negative 2 and not minus 2, because that's different on our calculators. 2/5, nope. Negative 2/5, nope. So all of these are a no so far. Alright, then we have 3, and negative 3, and 3/5, and negative 3/5. Wow. And 4, and negative 4, and 4/5. 4/5 works, yay! So, positive 4/5, meaning the factor is negative 4/5. And then did I do negative 4/5? Nope, that's not a 0. And then 6, and negative 6. So none of those. 6/5, negative 6/5. 12, negative 12. And 12/5. Nope, and negative 12/5. Alright, so then you're saying, okay, well, what are the rest of them? Well, now we will have a squared equation that we can then use the quadratic equation in order to find either the irrational ones, because clearly this was the rational roots theorem, or the imaginary ones. So, I'm going to do some synthetic division in order to take out this factor, and I'll do that on another sheet. So, I have 4/5 as the 0. And that's going to be synthetically divided into a 5, negative 24, 1, and 12. So we bring down our 5. 5 times 4/5 is just 4. Add those together and we get negative 20. Multiply negative 20 times 4/5, and we get negative 16. Add that to a 1 and we get negative 15. Negative 15 times 4/5 becomes negative 12, and so we get 0, which we knew we'd get. Which means that 5x squared minus 20x minus 15 is the quadratic equation that, when multiplied by x minus 4/5, will get us back to that original cubic equation. It also means, oops, that should be a squared, that our a value is 5, our b value is negative 20, and our c value is negative 15 in the quadratic equation of x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. But of course, instead of a b, we're writing negative 20. Over here, instead of a b, we're doing negative 20, whoops, that will be squared. And then our a and our c are 5 and negative 15. And then our a over here is, I suppose I could have factored out a 5, oh well. Alright. That means that everything can be evaluated, so negative 20 squared inside of the square root makes 400, and then that I'm going to add 4 times 5 times 15 because of all the negatives. Yikes, so square root of 700. So, officially we'll have 20 plus or minus, because negative negative 20, square root of 700 over 10. Super. And so we have two irrational zeros. I am going to see if I can simplify this, which I can, because square root of 700 is the same as 7 times 100. So we have 20 plus or minus 10 square roots of 7, which means that it's 2 plus or minus square root of 7 as our other zeros. So in factored form, we have x minus 4/5, x minus 2 plus the square root of 7, and then x plus 2. Oh wait, these are both plus. It's 2. This is what becomes different. There we go. Woohoo! Alright, so the zeros are that, and then They actually have linear factorization not in this piece, but they have it staying as x squared minus 4x minus 3 with a 5 out front because of each piece being able to be divided by 5. So if you have this answer, that's cool. If you have this answer, that's even cooler. Okay. Alright. Because technically that squared equation is not linear. So, alright, then I believe our last one here is write a polynomial function with real coefficients whose zeros and their multiplicities include those listed. Superb. So, alright, so degree 3, got it, so we'll need an x cubed in the end, which will happen because if we have zeros of a 2 here, that means that our factor is x minus 2. We also have a complex 0, which is x plus 1 plus I. But then we also have, because we have one imaginary solution, you have to have 2 of them always. So we also have x plus 1 minus I. You always switch the imaginary piece with being negative. So notice that the 1 stayed the same, but the I value, or the imaginary piece, became opposite. So a little easier to look at if we say x minus 2, x plus 1 plus I, and then x plus 1 minus I. Still not that helpful. So how do we make this into real coefficients? Because I is not. We would multiply these two pieces. So if we get ourselves a 3x3 box and put x1 and I, and then x1 and negative I, we can get all of our pieces of how they multiply. So x squared there, x, ix here, x, 1 times 1, I, negative ix, negative I, and then I squared. And I squared means, oh, negative I squared. So we have a negative, but then the I squared part is the square root of negative 1 and then that quantity squared, which when simplified leaves a negative 1, which is just 1. So very long way of saying that this is a 1 in this square. The other piece that happens when you put all of them together here is that you get an x squared, 2 x's. The xi and the ix that are negative cancel. We also have a 1, but then these also cancel, negative I and positive I, and then plus another 1 from this last circle, or box. So that means that we actually have x squared plus 2x plus 2, and that is going to be multiplied so that we can get the official polynomial by the other 0, which was x minus 2. So we have x cubed plus 2x squared if we multiply, 2x, negative 2x squared, negative 4x, and negative 4. So officially our final polynomial is going to be x cubed. These two cancel, so minus 2x for this combo, and then minus 4. And that is the equation that will end up having a degree 3, yep, and these zeros along with the one that comes because of it being imaginary. Yikes, that's fun. Okay.